Hello, God bless you, and thank you for watching my videos. Please like and subscribe to my channel, and if so moved, contribute to sponsor my research and ongoing scholarship via the PayPal link and or whatever other means I may provide in the future. This is a new series I am calling Geometric Binomial Algebra, now with improved production values. Ooh. This is part 1 and a good place to start. Integer valued polynomials. Let's consider a univariate polynomial of degree d. Univariate meaning there's just one argument, x. F of x is our univariate polynomial. If the degree equals 2, that is a quadratic equation and is most commonly thought of as ax squared plus bx plus c. But the a, b, and c are just coefficients, so to make things easier, we'll sometimes then go to a single letter with an index to indicate which coefficient it is. Here, a2 is a1 is b, and a0 is c. And that way the index matches the power to which the power of x to which the coefficient is multiplied. For any polynomial with positive integer degree d, let's consider the polynomial over all integer x. So obviously, if all of the coefficients, the a subscript k of a given polynomial of degree d, where k then runs from 0 to d, if all of these coefficients are integers and all of x are integers, then obviously all of the values f of x are integers. So f of x is an integer for all x. And if we wanted to consider the entire set of all such polynomials meeting these properties, maybe we call that set A subscript capital I. Now we can consider all polynomials such that f of x is an integer for all integer arguments x, and ask, are all these polynomials necessarily elements of the set AI? In other words, if not, then there's going to be some polynomials which have integer arguments and integer values, but the ak, the coefficients, are not necessarily all integers. So there are polynomials like that, lots of them, and so they are separate from AI, but yet they are still integer valued polynomials. So we have this additional set of polynomials not in AI for which ak, at least one of the ak, is not an integer but is still rational. And we can call this set A subscript R, capital R, for rational. Then the union of AI and AR is the set of integer valued polynomials. They have been studied extensively throughout the centuries, but it was Polya and most of modern references and work on it that we know of references Polya, early 1900s, who studied the various rings of integer valued polynomials. Note here that I did not mean to imply that AI plus AR is a single ring of integer of polynomials. In fact, that there is not a single ring, that the basis is sort of fractured is part of the charm and intrigue of integer valued polynomials. Polya is famously credited with showing that any given integer valued polynomial may be expressed as a linear combination of binomial coefficients x choose k, where k runs from 0 to d, in exactly one way. So a unique polynomial, a unique coefficient set, ck, will reproduce the polynomial in terms of binomial coefficients, as opposed to the canonical way of a linear combination of powers of x up to x to the d. So rather than coefficients times powers, x to the 0, x to the 1, x to the 2, Polya here has coefficients times the binomials straight from whatever degree row of Pascal's triangle. 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, etc. So that no matter what the degree, x choose 0 is always 1, x choose 1 is always x. Then there's the middle guts, and by the time we get to the end, we have x choose d minus 1 is x again, and x choose d is 1 again, so the symmetry there. There's a nice review paper from 2016 by Cahen and Chabert called What You Should Know About Integer Valued Polynomials. In the introduction, they give Polya's formula for his coefficient ck, and then they also mention, and they kind of say, well, and it's reminiscent of the Gregory-Newton formula from the 17th century. Now, Gregory-Newton expressed their formula for the coefficients in terms of the forward difference operator, versus Polya's formula with each ck determined by fk minus this squirrely little sum of the previous coefficients multiplied by binomial coefficients k choose I, versus Gregory-Newton, where the recursive definition uses delta k of f, which is defined recursively for each in terms of delta k minus 1. And Cahen and Chabert point out that Gregory-Newton's formula can be proven by reference and examination directly on Pascal's triangle and the binomial coefficients. If we write out Pascal's triangle as follows, the bottom row is a 0-degree polynomial, the second row up is a 1-degree polynomial, the third row up is a 2nd-degree polynomial, etc. In fact, the 2nd-degree row, the third row up, 2nd-degree polynomial, are the choose 2 binomials, 1, 3, 6, 15, etc. like that. So each row on this table of Pascal's written this way is a polynomial. And in fact, most papers that you come across studying integer valued polynomials will use these exact polynomials as the first example of integer valued polynomials for which the coefficients in terms of power expansions are not integers, so belonging to the AR group, except for the first 2 rows where d equals 0 and 1. This is because for all of these polynomials, the coefficients are always going to have a denominator of d factorial. So 1 for 0 and 1, and they stay integer, and then for higher degrees, 1 over d factorial is always going to be a rational but not an integer coefficient for like a0 or a d, especially because its numerator is always 1. So if we take this top row, for example, as our function, the 4th degree, or choose 4 binomials, it's a 4th degree polynomial, and so our first difference is going to be 5 minus 1 to give us 4, which goes down below in the x equals 2 spot. Or actually, x equals 1 is what I mean. And following the recursion plunks out this diagonal, which is the coefficients of a 4th degree power expansion. In this case, the expansion of the quantity 1 plus 1 to the 4th power, which of course adds up to 2 to the 4th power equals 16. And if we go through and prove the compute the coefficients via Polya's formula, we obviously we see that Polya's formula is the same formula. So I don't know if I'm taking crazy pills or what, but it's the same thing. In part 2 of this series, we're going to see that both of these are also pretty much equivalent to Vandermon's identity. So please check that out, and in the meantime, like this video, subscribe to my channel if you have not already, And please click on the PayPal link or whatever other means I may provide in the future and contribute to my further research and scholarship.